Quiz 2, One-Dimensional Kinematics. Many of you did not do well on this quiz, so you should, while you still have it in mind, go back and work through it and see the things that you should have known in order to be able to do it correctly. That's the purpose of this video. This is an interactive video. I'm going to ask you to pause the video at certain points and do things. So work along with me to make this most effective as possible. You should pause the video and, to the best of your ability, do what I ask you to do at each pause point. Then come back and check your work with what I do following the pause. So first, I'll let you, once you pause the video, carefully read through the problem as it's written above. I also want to point out the think, plan, do, check strategy. I don't think I've talked about this in class, but we're going to do this problem in 4 steps, and you're going to do the first 2 and this after the first pause. So the first thing, once you've read it, you're going to think through what you understand. Ask yourself questions like, what do I know? And what do I need to know in order to get the information? And once you've thought through the problem, then you come up with a plan, a preliminary plan. We can change it along the way, but you come up with a plan for the way in which you're going to solve the problem when you come to the do step. So think about the problem, and when you come back, I'll tell you my thoughts, and you can compare them to your thoughts. And I recommend that you write down what you're thinking. It can be in shorthand if you like, but it should be written down. You need to commit yourself to a definite thoughts about this problem, and then come up with as specific a plan as you can. It'll be subject to change, but you'll come up with a plan, and jot down notes or bullet points or steps 1, 2, 3 on your plan. Once you've done that, draw a first draft motion diagram. So draw yourself an inclined plane and show the position of the cart from time equals 0 to time equals 6 as to what you think it's going to look, what the motion diagram is going to look like, showing the position of the cart on the track every 6 seconds. So pause the video and do those 4 things. Read over the quiz carefully. Think about what you know about the problem. Make a plan for solving the problem, and do the first draft motion diagram. Okay, you're back. So you've read the problem, you've thought about it, you've put together a plan, and you drew a first draft motion diagram. So let's review what you thought about and planned and drew with what I did. So I thought there's an incline and it's flat, so there's going to be an acceleration, and the acceleration is going to be constant. And that means that the velocity is going to be increasing as the ball goes down the track. And so in order to get the positions and the velocities, I want to find the acceleration. And I remember from lab that we did this problem, and to get the acceleration, we need to know the final velocity, the initial velocity, and the time. So we know the time, we know the initial velocity is 0. We need to find the final velocity, and I also remember that the final velocity is not the average velocity. But remembering that what we did in lab was we took the average velocity and we doubled it, because v final plus v initial over 2 equals V average. And so V initial is 0. And that leaves us, if multiplying both sides by 2, that leaves us that V final is equal to twice V average. So that's my thoughts. And with the V final, I can calculate the acceleration. Right now I'm doing my plan. I've already started the plan. The plan is to get the acceleration and then use the acceleration to get the velocities, because if I know how fast it's accelerating, I can get the velocity it's each next second. We've done this a few times in class. And then knowing the acceleration and the velocities, I work my way back to figure out what the last step is. What is the position of each of these things exactly? Of course, we know the initial position is 0 and the final position is 150. So with that in mind, we're going to pause again and try and put together the data table. Okay, you're back. You've done your calculations. You've put them in a data table. Let's see what you did and what results you get. First, you calculated V average. And that's delta x delta t. T. X final minus x initial. 150 centimeters minus 0 over 0 minus 5 minus 0 seconds. The delta t is 5. This gives, that seconds gives us 30 centimeters per second. That makes the V final 60. Can't fit it, but what it is, centimeters per second. Now we can get the acceleration. So the V final would be 60 centimeters per second. I'm not going to try and write the units. Minus 0 over the 5 seconds. That gives us 12 centimeters per second, or 12 centimeters per second squared. Okay, I'm going to go to slide 2. So note the data table copied in the slide. You can see the acceleration, 12 centimeters per second squared everywhere. The acceleration is constant because the slope of the incline is constant. And so from that, you shouldn't really need the equation. You should think this through. But you can use the equation if you want. The acceleration is 12 centimeters per second. The velocity starts at 0. Now notice, when the velocity is 0 and the thing has been released, the acceleration, even when the velocity is 0, is 12 meters. You don't put a 0 here. That's important. Okay, so every second, the velocity increases by 12 centimeters per second. So it goes from 0 to 12, 24, 36, 48, 60. That's what we calculated for the final velocity, 60. So that's good. That's an agreement. And if you insist on using the equation, then use the equation. Whoops, let me get my pen. V final equals V initial plus AT. So V final equals, in every case, 0, plus the acceleration, 12 centimeters per second squared, times the time. So times 1 second, times 2 seconds, times 3 seconds, and then you get, in that case, all these different velocities that you see here. Okay, now the distance takes a little more thought to calculate, but you might remember the way we did that in class is we would take the average and multiply it by the time. So you see during the first second, from time 0 to time 1, the velocity goes from 0 to 12. So the average during that interval is 6. And if you multiply 6 times 1 second, you get this, 6 centimeters. Now if you go to the second and you take the interval from the beginning to second 2, 24, in that case the average is going to be 0 plus 24 divided by 2, 12. So an average of 12 over these this 2 second interval, 12 times 2 is 24. And if we continue that, you generate the rest of the numbers. And I've positioned the cart so that they are at, start at 0, go to 6 centimeters, go to 24, 54, 96, 150. If you wanted to use the equation, you would, there's two equations you could use. You could use, what I'm using is that, let me get my pencil. I'm using the equation off the equation sheet that says delta x equals v final plus v initial over 2 times the time. You have that equation. That's the one I use, doing it in my head. You could also use delta x equals v initial t plus 1/2 a t squared, where v initial will always be 0, and this will generate the same numbers. I'd rather you, when you can, you think it through so that you're fully understanding what's going on. Now once we have those numbers, we use those to make the motion diagram, and then we use them to do the plot. And you see the plot here. The green triangles form a parabola. That's position versus time. And the red squares are the velocity. That's a straight line. Velocity versus time. And the acceleration's constant at 12, and you see all the values for acceleration constant. That's a straight line with 0 slope. And just to remind you some of the characteristics of the graph, at any point the slope of the parabola is the velocity. So you see the slope of the parabola in the beginning is 0, and the slope of the parabola at the end would be 60 centimeters per second. And you see the velocities climb linearly, 0, 12, 24, 36, 48, 60, and the slope of this line, the change in y over the change in x, or in the case of the velocity, the change in velocity over the change in time, that's the acceleration. So the slope is constant. There's a slope of 12. That gives us the acceleration, a value of 12. And I'll go briefly to the next slide. And in this case, you can see the points connected by lines, so you can clearly see the green line is a parabola. The red line is a straight line with a constant slope of 12, and the acceleration is constant at 12 centimeters per second squared. We're done.